This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 5, Heat Exchangers Part 2, the Effectiveness-NTU method. Last lesson used LMTD, which needs both hot and cold terminal temperatures. The moment an outlet temperature is unknown, that method forces you to iterate. Effectiveness-NTU avoids it. Build the capacity rates, form NTU and the capacity ratio. Read effectiveness off a single curve, and recover the heat duty and both outlet temperatures in one pass. We finish on plate and frame exchangers. Concept 1. What effectiveness measures? It is the actual heat moved divided by the maximum a same inlet exchanger of infinite area could move. That ceiling belongs to the minimum capacity stream carried across the full inlet temperature gap, hot inlet minus cold inlet. Because the numerator is the real duty either stream gives it, effectiveness always lands between 0 and 1. Concept 2. Method choice, and it is a favorite exam decision. If you know all 4 terminal temperatures, you are sizing an exchanger. Use LMTD. If an outlet temperature is unknown, you are rating a given exchanger. Known UA, inlet temperatures and flows. Use Effectiveness-NTU. Forcing LMTD onto a rating problem means guessing an outlet and iterating the log mean. The effectiveness method reaches the answer in one pass. Concept 3. The framework. Each stream carries a capacity rate, mass flow times specific heat. The smaller of the two, C-min, caps the possible duty. NTU is a dimensionless size, area times the overall coefficient divided by C-min. And the capacity ratio is C-min over C-max. Those 3 groups, C-min, NTU, and the capacity ratio, are everything the method needs. Setup. The relations. Effectiveness is a fixed function of NTU and the capacity ratio for a given flow arrangement. 2 cases cover most waterside equipment. A phase change stream, a condenser or evaporator, has a capacity ratio of 0, and effectiveness is 1 minus e to the minus NTU. A counterflow exchanger uses the fraction on the left, with the balanced case collapsing to NTU over 1 plus NTU. On the chart, every curve climbs with NTU toward 1, and a higher capacity ratio pulls it down. The balanced exchanger is the least effective at any given size. Setup. A plate and frame rating. Hot water at 200 degrees is cooled by cold water entering at 60 in a counterflow plate and frame unit. We know both flow time specific heat products and the overall conductance, but neither outlet temperature, a rating problem. Plate and frame units aren't sized by a printed handbook formula. They ride this same Effectiveness-NTU framework, just with a high overall coefficient and a close temperature approach. Let's rate it. Solve. The capacity rates are 2000 and 4000, so C-min is 2000 on the hot side, and the ratio is 1/2. NTU is the conductance over C-min, which is 1. On the counterflow curve at NTU 1 and ratio 1/2, effectiveness works out to 0.565. The maximum duty is C-min across the full inlet gap of 140, times effectiveness gives about 158,000 BTU per hour. Back out the outlets. The hot stream leaves near 121, the cold near 100. The hot stream, having the smaller capacity rate, swings the larger temperature change. A word on plate and frame exchangers. Stacking thin corrugated plates packs enormous area into a small box, which drives the overall coefficient and the area up, pushes NTU up, and lets effectiveness approach 1. So you get a very close temperature approach, only a few degrees. That is why plate and frame units dominate water-to-water hydronic and district service, and why they unbolt for cleaning and expansion. There's no separate sizing formula in the handbook. You rate them with the same Effectiveness-NTU framework we just used. Traps. 4 ways this bites. 1. Reference effectiveness to C-min and the full inlet gap, never to C-max or a single stream zone change. 2. NTU divides by C-min, not C-max, the most common setup slip. 3. A condenser or evaporator has a phase-changing stream, so its capacity ratio is 0, and effectiveness is 1 minus e to the minus NTU. Don't force it into the counterflow ratio form. 4. If you already know every terminal temperature, your sizing, use LMTD. Save Effectiveness-NTU for when an outlet is unknown. Quick recall. Build C-min from the two capacity rates. Form NTU as conductance over C-min. Form the capacity ratio, and read effectiveness off the relation for your flow arrangement. 1 minus e to the minus NTU for a phase change, the counterflow fraction otherwise. Multiply by C-min and the inlet gap for the duty. Then back out both outlets. The trigger is always an unknown outlet temperature, and everything references C-min. Next up, Lesson 6, Chillers and Condensers. We've rated the exchanger. Now we turn to the machine that rejects the heat. We'll work the water-cooled condenser, condensing water flow and tube side pressure drop, and the chiller efficiency metrics, EER and COP. Then contrast water-cooled, air-cooled, and VRF units at the concept level. Everything's at PEPrepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.